Hello, my name is Zheng Chen from Indiana University Bloomington. Our research is about to predict partially observed map structure using low-rank matrix completion. We solved the map prediction problem in the task of coverage mapping for urban and residential environments. We observed that those environments usually have a strong structured pattern, such as road network and building layout as shown in Figure 1. Those patterns are typically presented by some linear dependent structures that can be modeled as maze maps, one example of which is shown in Figure 2. In this work, we carefully examine the properties of the maze maps and find that maze maps usually are low rank and have incoherent structures, as shown in Figure 3 and Table 1. Incoherent structures mean that the coherence value of the matrix is low and the value of the elements are more likely to be spread through the whole matrix, instead of concentrate on some local region inside of the matrix. With the low rank and incoherent properties, a partially observed maze map, such as those shown in Figure 4 and Figure 5, could be predicted using low rank matrix completion with theoretically proved near perfect accuracy. In this work, we mainly have three contributions. The first one is this is our first time to examine and report that many complex urban and residential environments possess low-rank and incoherent structure, and to apply low-rank matrix completion for map prediction. The second one is our proposed low-rank matrix completion-based map prediction outperforms another state-of-the-art map prediction method, Bayesian Hilbert mapping, in terms of prediction accuracy and the computation time, such that our method is able to perform dense prediction in real time. The last one is we have performed extensive simulations and demonstrated the remarkable effectiveness of our proposed method. Low-rank matrix completion is defined to complete a partially observed matrix whose corresponding ground truth matrix has a low rank and an incoherent structure. Mathematically, we formulate this process as an optimization problem, that is to find a minimal rank matrix that is consistent with the partial observations. Specifically, the problem is formulated as this, where the matrix X is a predicted matrix. The matrix M is an observed matrix, and omega is a set of observation locations in the matrix. Unfortunately, the original form of the rank minimization problem is non-convex and NP-hard. An alternative way is to use nuclear norm of the matrix X to approximate the rank of X, such that the optimization problem will turn to be a convex problem. However, the constraints of this convex optimization aim to exactly recover the matrix. This might be too rigid and could easily result in overfitting to the observed elements. A more robust way is to add a regularization term which tolerates some level of error. Equivalently, the problem could be reformulated into a Lagrange form like this. We use a soft input algorithm proposed in the reference paper to solve the nuclear norm regularized least squares problem. In this paper, we use a TSP-based non-myopic planner to get the robot for coverage mapping. Before we compute the path, we need to determine the number of waypoints. It has been proved that the number of sampled entries to perfectly recover a matrix has a lower bound. Accordingly, the placements of waypoints can be defined as this, where n is the number of observed locations within the robot sensing range. Since robot can take observations in between any pair of consecutive sampling waypoints, this can introduce additional observations. This means the actual number of waypoints for TSP can be further reduced, and we use epsilon as a scale factor. In the experiment, we compare the map prediction performances of our proposed low-rank matrix completion and the baseline, Bayesian Hilbert mapping. Here, we show the prediction results on an urban road network map with two different observation modes. The first row shows the results with noisy observation mode, while the second row shows the results with partial observation mode. We can see that our low-rank matrix completion-based method can predict the near-perfect map and significantly outperform the baseline Bayesian map in both observation modes. To further quantitatively show the advantage of our proposed method, we conduct extensive experiments. We first show the results with noise observation mode. The left two pictures show the accuracy and time statistical results with different value of epsilon on 20 different mazes that have the same rank. From the trend of the curves, we can see that our proposed low-rank matrix completion-based method can achieve higher accuracy but with a significantly lower computational time. The right two pictures show that the results on different maps with different rank values, and we still see the same trend. Next, we show the results in partial observation mode. Similarly, we can see the same trend as in noisy observation mode. The experimental results have validated that our proposed low-rank matrix completion-based method is more accurate and faster. In some application scenarios requiring dense prediction, such as coverage mapping tasks, the low-rank matrix completion method can be used in real time, while Bayesian mapping might be too slow to work. Here, we show the coverage mapping process on an urban road network map in left pictures and compare coverage mapping convergence performance per action step for different coverage planning methods in the top right pictures and the bottom right table. From the data we have collected, we can see the proposed low-rank matrix completion-based real-time map prediction method can achieve a much faster mapping process and can be easily plugged in any planning method. In this video, we show more details related with our work. We first present the comparison of the results with and without map prediction for different coverage planning methods. As can be seen, the combination of map prediction and TSP planning can achieve a faster coverage mapping with high accuracy. We also conduct a real-time urban road network coverage mapping and real-time terrain mapping. The results show that our proposed real-time map prediction method can significantly facilitate the mapping tasks, even in complex environments. Thanks for watching, and any question is welcome.